All right, thank you, ladies and gentlemen. It's 8:09 p.m. on Friday, May 20th, 2022. Our speaker tonight is Mr. Awanish Mishra, one of SVAS's newer board members, is a man with a distinguished career in science, who will be presenting on astronomical distances and the measurement thereof. And without further ado, Awanish, the floor is yours. You may share your screen and get started.
All right. Well, thanks a lot, Raj. Let me just set up and share my screen. Can everyone see that screen? Good. Just
yes.
Excellent. Okay. Well, I'll go ahead and get started. That is my poor man's version of the eclipse last week. That's about as good as I could get it. So unfortunately, it wasn't a great evening. So astronomical distances is what we're going to talk about tonight. My name is Awanish Mishra, and I am thrilled to be here. I wouldn't say so much a distinguished career in science, but I love science. I love physics. I love chemistry. And any chance I get a chance to talk about it, I will take it. While we're here, we're also going to talk for a little bit at the end about black holes, a little update on what they are, their structure, and ultimately the imaging of Sagittarius A star by the Event Horizon Telescope. This is our black hole at the center of our galaxy. Just a real quick about myself. I come from Minnesota, and I spent quite a few years, in undergrad and grad school, working in chemistry and physics, and I did my graduate degree in quantum mechanical modeling. And but now I'm retired, and I try to go to cold places whenever I can. I'm not a fan of California weather, never have been, not since 1973, since I've lived here. But I do love my beagles and my wife. I got to put that in there, and I'm thrilled to be here. So that's a little bit background on me. I did spend a few years doing nuclear research as well, looking at the effect of an atomic bomb explosion and how strontium-90 can do bad things to your body. So that was an interesting time. Anyways, tonight's agenda is going to be, we're going to talk about the vastness of space, measuring astronomical distances, and then looking a little bit about our place in the universe. And because of recent events, I want to do some current events related to black holes and the imaging of Sagittarius A star. Okay, so we'll go ahead and get started. And like I said, at the end, I can take as many questions as you have, but if someone feels the need to really need something clarified, or I goof up something, you feel free to chime in and ask or comment, and we'll go from there. But preferably towards the end would be better. So first and foremost, before we can talk about distances, we need to understand, or I think we all do to some degree, that the universe is unimaginably large. And basically, space is vast. If you think about it, Earth has a diameter of about 7,900 miles. By the way, I'm going to use miles, I'm going to use kilometers, sometimes one right after the other. Don't let that bother you. It's just kind of the world we live in. Big chunk of my life was all in the metric system, and then a big chunk of my life has always been in the imperial system. So I kind of move between the two, but I'll keep it clear. And Earth averages about 93.5 million miles from the sun. Okay, so that's pretty far distance. The Kuiper Belt is up to 4,675,000,000 miles away, and beyond that, there's the Oort cloud, which is 18,700,000,000,000 miles away. So these are incredible distances. Think about it, thousands, millions, billions, trillions. But as it turns out, that's barely even scratching the surface when it comes to appreciating the distances involved in the universe. So basically, astronomical distances are ginormous, and that is a technical term. It's a huge amount. Our day-to-day scales, the rulers, the yardsticks that we use of the inches, feet, meters, yards, leagues, nautical miles are inadequate. not just inadequate, but completely inadequate. And so in order to look at astronomical distances, astronomers use a new set of rulers, their own set of rulers based on much larger scales. First, there's the astronomical unit. Okay, the average distance between the Earth and the Sun, as I said, is 93.5 million miles, about 150 million kilometers. And that's what we call one astronomical unit. That's a pretty good yardstick to measure things around within the solar system. You know, Pluto is 39.47 astronomical units from the Sun versus saying 3,669,000,000 miles. Now you may think, oh gosh, you know, who cares? You know, well, it's easy for me to say the local Safeway is 2 miles away. That sounds normal, like AU for planets, but it would seem kind of goofy for me to say it's, you know, 10,560 feet away. So you can see where it makes sense to use the right kind of ruler, the right kind of measurement stick. There's also the light year, which is the distance that light travels in a year, which is about 5.88 trillion miles, about 5.9 trillion miles. That's a lot of distance there. Light from the sun takes 8.3 minutes to reach us, so it's 8.3 light minutes away, meaning traveling, the energy it expels, the photons are traveling at 186,000 miles, 282 per minute per second, and it takes it 8.3 minutes to reach us. And Pluto happens to be, instead of saying 39.47 astronomical units, it's 13 light hours away. And the closest star system, now I'm not saying the closest star, the star system, Alpha Centauri, is 4.3 light years away. So if you could travel at the speed of light, as you well know, it would take us 4.3 years to get there. And then there's parsec, and which is another measurement oftentimes used by astronomers. It's about 3.26 light years away. It isn't a measurement of time, okay, as it was mentioned in Star Wars, but it's 3.26 light years away, and it's derived from parallax second. So if you break up, if you're looking at a star and you break up down to 1 arc second, a second, that's 1/3600th of a degree, and that'll subtend across 3.26 light years. So that's a parsec, or about 19.2 trillion miles. So the closest star system is now 1.3 parsecs away. Now, these are great measurement rulers, but what about us? You know, humans. Humans have physically traveled. When you think in terms of AU, light year, parsecs, and so on, we've traveled about 1.3 light seconds from Earth. In other words, we've gone to the moon. And that's as far as we've gotten. So when you think about Pluto being so far away, or you know, 4.3 light years to get to another star system, and the most that human beings have traveled is 1.3 light seconds away. That's it. But our technology has gone farther. As of this morning at 8:36, Voyager 1, the way NASA will display it is 44 years, 8 months, 15 days out, and some 2 hours, 40 minutes, and 45 seconds at that time. So it happens to be 14,468,000,000 some odd million miles out there. And distance from the sun is 156.43 astronomical units. I actually subscribe to its Twitter feed, and every day it tells me how many one-way light time. At that time, it was 21 hours, 34 minutes, and 29 seconds away, or about 21.57 light hours away. And that distance puts it outside of our solar system, finally. So just to get out of our solar system, not even to the Oort cloud, just to get out of our solar system, it took it 44 years. At that speed of 38,026 miles per hour, it'll take it, well, it's traveled to 0.002461 light years. If you convert that to get to the nearest star system, which is 4.3 light years away, it's going to take about 76,000 years. So as fast as 38,000 miles per hour is, it's nowhere fast enough to get us anywhere reasonable outside of our solar system, let alone to the farthest reaches of our solar system. Voyager 2 is close by, but heading out in another direction. It's also alive and doing well. But so there are these distances that are just within our own backyard, our own front yard, you know, and we haven't gone anywhere yet. But to get further out, we need to be able to not only understand how far away they are, but we've got to be able to measure it. So distances within the solar system, you know, can be measured using lasers and radar, typically. The round trip time taken is reflected back, and of the pulse, you cut that time in half to get the distance. Distance is velocity times time. So you take that time, multiply it by the speed of light, because whatever signal you send, whether it's radar or laser, it's going to move at the speed of light. So that's its velocity. Reflectors on the moon allow laser beams to accurately measure its distance at any given time. In fact, it can measure the distance to the moon within a few millimeters now. And the moon is moving away every year at about 1.5 centimeters per year. And it's measuring that on a regular basis. Radar can be used similarly with nearby planets. We can bounce off radar signals and measure the inner planets and even get a little bit further out. But radio signals are also used, especially with our probes. And by looking at the time difference each time we communicate with it, we can also determine how far away it is, how fast it's moving, things like that. The NASA Deep Space Network, this is a really interesting site. You can go there at any given time and look at, you know, how things are in Madrid, the Deep Space Network locations, Goldstone, California, and in Canberra, Australia. And here, when I checked this morning, it was talking to various probes, including James Webb Telescope, Mars Reconnaissance Orbiter, and others out there. And oftentimes I'll even see it talking to Voyager. So you're able to look at it in real time as to what's happening, what the light time is, and so on and so on. So there's a lot of good information available out there if you're interested in finding out what we're doing with our probes and where they're located and how far away they are. So this method works to about 1 billion kilometers. Further out, radar and things like that the signal becomes much more degraded and it doesn't seem to work that well. So, but for further objects, further away, we have a whole bunch of other methods that are available to us. And I'm only going to be talking about the common methods like these. There are other methods that, you know, to do the same thing to different degrees of accuracy. So, but I won't get into every method out there. Well, one of the interesting methods is known as triangulation parallax method. Now, the reason this one is really important to understand is it's been known for a long time because human beings are biologically evolved to use parallax. We have two eyes that are separated by about 3 inches, right? So that gives us binocular vision. Now, if you stick your finger out like in this image here, and you look at it with one eye closed, you see that there's a little bit of a shift between the two. And if you can understand that, if you can figure out that angle between the two, you can calculate distances. And that's a very easy way to use basic trigonometry to figure that out. And having 2 eyes also, you know, allows our brain to quickly process the image that we're seeing in stereo and then determine depth and allow us to move forward more easily. But that's 2 eyes that are separated by 3 inches. You need to apply that to an astronomical scale, but you can't eyeball it, right? Obviously, You're not going to be able to look at a star with one eye or the other and be able to see any difference. Heck, yeah, you can't even easily do that with, I don't think you can do that with the moon. But there is a neat thing you can do. You can look at the Earth, and when the Earth is on one side of the sun in December, say, and then on the other side of the sun in June, now you've got your two eyeballs. Here they are, and you can look at the star of interest at both times and be able to measure that angle. And then it's a matter of simple geometry. The things of interest are going to be the star, Earth, and the sun. And with that, you can form a right triangle. And here's the cool part. You know what that distance is, known as the opposite. Well, that's going to be one astronomical unit, right? The average distance from the sun to the Earth. We can figure out that angle alpha. And I know it sounds, I'm getting into math, I'm not, but just show you how easy this thing is going to be. What you're after is this thing called adjacent. I specifically picked those names. Well, in trigonometry, adjacent is equal to opposite over the tangent of x. Plug that into your calculator. Ask Siri, ask Alexa, they'll do it for you. Now you can plug it into on Google and they'll handle that for you. So that is a really easy and a very cool way to measure how far away a star is. Okay, and that works nowadays. It was initially good for about 100 light years. It works to about 1,000 light years now, which is pretty amazing. And that's one of the ways we determined, that was the way we determined how far away the Alpha Centauri system is located, 4.3 light years. So that's a great way to within 1,000 light years, but that's not anywhere yet. We haven't even gotten out of our neighborhood of the solar system. So there's another method called the brightness method. And it uses, it looks at the brightness of a star and it looks at the spectrum of the star. And mind you, in the parallax method, that's more of a direct measurement. We're looking at angles. And we know the spectrum of the star because we can measure the spectrum, and we're able to calculate its distance and know how it behaves when it's that far away, how bright it is, regardless of the distance it's at, its apparent brightness. And that's important here because the spectrum will also tell us the absolute brightness. You don't need to worry about what the heck does that mean, the details around it. What it means is if we can take a spectrum, which we can, then we know exactly how bright that is. In other words, how bright is a 60-watt light bulb when you're looking at it in arm's length? Now, you can qualitatively understand that. Now, if that same light bulb is 300 feet away, it doesn't look nearly as bright. Its apparent brightness is something else, not its absolute brightness. Well, with stars, you can look at the spectrum and determine that. And then you can look up the luminosity of the spectra of nearby stars from that whole catalog of the parallax method and other sources that we have. For example, like here's the spectrum of the sun. Now, the reason that's important is if we know, oh, here's the spectrum of an unknown star, we can compare it with, well, here's what it matches up with our sun. So it's a similar star. We know its absolute brightness. And because we know it's a certain type of star, we know how big it is. We know a lot of things about it. But how does it really look to us from where we are? Well, it should be this bright, really, but it's only this little bit of a twinkle. And from that, we can calculate the distance. Because the apparent brightness is equal to its luminosity, the absolute brightness, divided by 4 pi d squared. So the distance is simply that simple equation. Just take the square root of the luminosity divided by the apparent brightness and multiply that out by 4 pi and take the square root, and it's easy enough. Well, there are a few more variables involved here. So it's generally accurate, but it's building upon previous methodology. And so it could be off by 0.01%, that type of thing, but it's still very accurate, and it works for most of the stars in the galaxy, which is great. Now you think about it. So here we are. We've got lasers and radar. We've got parallax method, and now we got this brightness method, and we've got the galaxy covered. Then, less than 100 years ago, we figured out that the universe is not just our galaxy. There's more stuff out there. To get further out, we use another method known as the Kefia star method or Cepheid star method. I'm never sure how to pronounce that, but these are special stars that brighten and dim on a regular basis. I think the origin of that is that as protons are absorbed, helium is built up, then it's shed, and that causes the brightness, and it dims back down, brightens up. Now, this pulsation period, as it turns out, is related to its luminosity, which is the absolute brightness. So wherever it is, if we see one of these little stars get brighten up, and then dim back down, and we can see it do this on a periodic basis, then we know its period of brightening up, pulsation period. And from that, we can figure out its luminosity. But this is an incredibly laborious process when it was first being developed. And it takes a lot of patience and great deal of fatigue and just perseverance to look at thousands and thousands of glass photographic plates in the late 1800s and the 1900s to be able to get to that data. So this was a lot of the work was done by a group of women at Harvard University, known as basically as human computers. But this is Henrietta Swan Leavitt. She never got really any credit for it until about the last 5 to 7 years or so. And she did a lot of this work to determine the correlation between luminosity and the Cepheid or Kefia star brightening period, which was an incredible standard candle technique that she worked on helping develop. Unfortunately, the people she worked for, they got all the credit and she didn't until recently, but I wanted to point that out. But here's the thing, if we know it's period, then we know it's absolute, luminosity. So big stars, massive stars take longer to pulse and other stars take shorter. There's also known as RR Lyra stars, which I'm not going to really get into here. They're great for determining the distance to globular clusters, and they're small, much more dim stars that do the similar thing. So they are small, relatively speaking. But this methodology is extremely powerful. And so by knowing, again, that luminosity based on its period, if it pulses every 5 days, we know it's about 1,000 solar masses. Well, we know what 1,000 solar mass is going to look like. We can even look at the spectrum and determine a lot of details around it. So now we have the luminosity, and we know what it looks like to us from here. And the apparent brightness we can calculate for D once again. And I know it's kind of a high-level, simple way of looking at it, but this is basically how it works. And this method works to about 50 million parsecs. So 50 times 3.26, about 163 million light years away. So the closest galaxy to us, or the big galaxy close to us, is about 2.5 million light years away. And that's Andromeda, M31. There are other ones too. There's also Triangulum. There's a bunch of other ones in our local neighborhood. But that being said, we can get out to 163 million light years by this method. So that's a decent slice of the universe, but it's like a diet slice of the pie, really thin. When you think about it, the universe is billions and billions of years old. So there's another method that's actually even cooler than the Kefia method, and that's known as a type 1 supernova. So type 1 supernovas occur in binary star systems. Fortunately, there's a lot of binary star systems out there. Earlier, I was mentioning the Alpha Centauri system, not star. There's Alpha Centauri, there's A, B, and there's Proxima Centauri. It's a trinary star system. So that has 3 stars in it. But fortunately, there's a lot of binary systems. But it involves binary systems that usually has a small dead star, like a white dwarf, meaning a star around our sun size that's dead. And when that happens, our sun will one day, not one day, but in about 4.5 billion years, begin undergoing its death cycle, and ultimately it'll die as a white dwarf, meaning it'll fall apart but retain most of its mass and compress down to the size of Earth, and then just glow until it dies into a cinder block trillions of years later. So they're out there. So here we are, having this dead star next to a living companion star is a good thing for us. What happens is these types of stars, they collect mass and suck it in from the companion star, and they reach 1.44 solar masses. It's a specific limit, and then they explode, or they shed. They don't explode completely. Then they shed all that material and light up the entire galaxy. They can become brighter. They don't light up their galaxy. They can become brighter than their galaxy. So because it's 1.44 solar masses, we know what kind of a companion star this dead star is. We know its absolute luminosity when it exploded. And then we look at our old friend, the apparent brightness. And once again, that equation will apply for us. So by measuring that, we can go back to this equation, and here we are. Now we found how far away that galaxy is, and that's what we're out there looking at when you're way beyond our own galaxy here. So this is useful for distances of 1 million parsecs to 1 billion gigaparsecs. In other words, 3.26 billion light years. Now, when you know that the universe is, around 13.8 billion years old, now you're starting to cook with gas here. Think about it. We're almost a quarter of the known universe. Extremely powerful tool. So we built up from this ladder and builds upon the previous one. Now, some people have said, well, what happens if we find out something is wrong with some of the earlier methods when they feed into new ones? Because ultimately they're going to go back to spectra and things like that. At this point, I've heard more than one astronomer say, if that were to happen, you're talking about changes of 0.1% or something. So it's not going to be significant. And at least for our needs, for most of our scientific needs, if something is 3 billion light years away or 2.995 billion light years, I don't want to speak for an astronomer or astrophysicist, but that's not going to make a huge difference today. So now we've got a way to measure galactic distances. And so this is a pretty powerful and widely used method. To get even further out, there are other methods, but one of the common ones is use Hubble's law and galactic Doppler shift to measure speed and distance. Here, what we've got going on is, let me just do something. Bear with me just for 1 second. Okay, so using Hubble's law, which basically said velocity is equal to Hubble's constant times distance. Okay, okay, thanks for sharing. But what that means is the value of the Hubble constant we've known, even though it's been debated. So that's one piece of the puzzle. And if we can understand velocity, we can get distance. Okay, so the Hubble constant, H0, is known as the proper Hubble constant, is debated or changes with time. For example, over the last few years, it's varied from 72.5 to 77.5 to all kinds of things in between. And we're coming up on 2022, so it's somewhere in this range. The point is, Hubble's constant seems to change a little, or our tools are really very, very different, more so than they should be. But we're trying to get an accurate measurement at any given time. Currently, it's about 73.4 kilometers per second per megaparsec, plus or minus 1.1 kilometer per second. So that means if I'm here and something is moving away, moving at 3.26 million light years away, it's moving at 73.4 kilometers per second, which is pretty fast when you think about it from me. But if it's moving, if it's 2 megaparsecs away, it's moving at 146.8 kilometers per second away from me. So understanding that motion, or understanding that speed with which things are moving, will be able to tell us how far away they are. And the way you do that is with Doppler shift. What does that mean? Well, it means the following. It's analogous to a car approaching, or a train. So, for example, if you're sitting in your car next to the train that's coming by really fast, or a car even, you hear it go, eeeew. In other words, as the pitch gets higher and higher pitch until it passes by you, then you hear a lower pitch. Okay, and that's the similar technology used in a radar gun when police are looking to see how fast you're going. They'll point it towards you as you're approaching, and they'll bounce radar signals off of you. Look at the frequency of the signal that comes back, its pitch, and as it moves away, they can also determine how fast you're going by looking at the same frequency, by calculating that frequency. Well, in astronomy, blue shifted objects like stars, galaxies, etc., are approaching us. Okay, now let me explain what blue shift means in a second here. Red shifted objects they're receding away from us. Okay, so what does that mean? Well, when something like a star is moving away from us, it has a lower frequency and longer wavelength. So that's shifting towards lower frequency, longer wavelengths is red part of the spectrum. Now, if it's coming towards us, whereas with sound, it would be a higher pitch, more of a whiny, whistly sound, then it's going to have a higher frequency, and this wavelength will be shorter. And that's shifting towards the blue end of the spectrum. So that's known as a blue shift. So this is what they mean by Doppler shift. It's easy, and that's how cops go after with radar guns. What you hear when you hear trains and cars, that's from sound waves. Similar things apply here. So we're able to determine, based on how an object is moving away from us, or if it's coming towards us. And as I mentioned in a second ago at the top here, cosmological Doppler shift data helps prove that the universe is expanding. The universe is expanding, and everything is redshifted. And we look out there. There's a few things that aren't, like Andromeda's coming towards us. In our local neighborhood, we're all a little more gravitationally bound to each other. At the local level, there may be some things like that occurring, but overall, the universe is expanding. We look out there, that galaxy way out there is redshifted. That globular cluster is redshifted. That other galaxy is redshifted. Everything is redshifting. So the extent of the spectral shift. So how do you measure that? You look at its spectrum again. How do you know that that galaxy is redshifted? What do I do? It's light, it's so dim. You can look at its spectrum. And what happens here is the following. If this is how different elements are identified by these black lines, this could be, you know, this yellow could be a sodium D line that typically occurs at a specific frequency or so many nanometers wavelength of light. But it turns out that you're getting that same spectrum, but everything is shifted towards the red a little bit. Well, you can still identify it. At first, when they saw this, they're going, what's wrong? Why are these spectra kind of off? But they still match up relative to each other. So we learned that they were moving away from us. That's redshifting. If this is us here, we're looking at a galaxy whose spectra should be this, but it really is this. It's moving away from us at a certain speed. And if it was coming closer to us, these arrows would point downward towards the blue, and that would be blue shifting. So that's how that method works. And you can plug that in using a more complex equation. And from there, you're able to look at different frequencies. Now, this is a simplified version. They will take relativistic effects into account and other things. But the point is that you can use this method, plug it back into here, and you get that distance is equal to velocity over Hubble's constant with this fractional Doppler effect. That's a Doppler shift ratio, and plug it all in there. You know the velocity of the spectra and of the photons are going to be the speed of light, and from this determine their distance. And this will take you out to the farthest reaches, billions and billions. Now, there's a few caveats, and I'm not going to get into all of them, but one, which is Hubble's constant seems to be changing with time, or by whoever's calculating with whatever tool they're using. So if you don't have a good grasp of Hubble's constant, you're going to get errors, you know. But again, if something is 13 billion light years away, or 13.1 or 12.9, how much of a difference is it going to make? Well, it could. Of course, if you're starting to look at things that, 100 million years or 300 million years after the Big Bang, then you're going to want to know things a little more accurately. And so there's this huge push to really understand Hubble's constant, Hubble's law, and other techniques. There are other methods related to the cosmological background radiation and microwave background radiation and other things that they can use to get relatively more precise information. But this works pretty well for most uses. So we've gone from bouncing lasers off the moon, or a cop using a radar gun on me at Interstate 80. Oh, it's been 8 years since I got a ticket, so crossing my fingers now. Yeah, at least 8 years. So all the way to looking at Hubble's constant to figure out how quickly galaxies are moving away from us. And they're moving away very, very fast, by the way. As someone pointed out here, 73.4 kilometers per second, as Raj mentioned, is 164,000 miles an hour. And remember, Voyager's the fast one. It's not the fastest we've got. The Parker Space Probe moves a little faster, is moving at 38,000 miles. Even if we double that, 64, that's still not allow us to catch up to the recession velocity of galaxies. Hopefully that makes sense. So now we've got this stepwise, one methodology after the next that gets us to the target that we're after. We want to know within the solar system, within the galaxy, within the local neighborhood, across the galaxy, to the ends of the universe. We have these techniques. Bottom line is, once again, the universe is unimaginably large. Fortunately, astronomers and astrophysicists are extremely bright and imaginative. And that's not easy for me to say, because I'm more of a chemist and physicist than I am an astronomer or astrophysicist. But I got to tell you, there are a few guys more bright and imaginative than these guys. Everything we do, think about it. And this is the thing that blows me away. Everything we do it from this location, our planet. We can't really go out there. Oh, sure, we've got a little probe out there, a few of them out there, but in general, it's all done from right here. And we've learned so much about the universe. So anyways, distance measurement tools are built on the results of other tools. So if there's a problem with one, it could have a cascading effect on others. It's a continuous improvement process. That's an old term, but it's true. So again, in summary, you've got radar within the solar system, parallax within 1,000, I should say light years, not stars, Milky Way galaxy, Kefia, 100 million, 200 million light years, and then into the billions, type 1a, and then even farther. And like I said before, there are other methods as well. So that covers a lot of what I wanted to say about how we measure those distances. Now, each one of these methods requires a laborious amount of work, a lot of work, and it requires a lot of math, and it requires a lot of patience. But we're rewarded. We live in a great time when we can know so much about the universe and how fast things are expanding, where we came from, where we're headed, type of things. So it's amazing what these types of techniques will do for us. I want to talk a little bit about, before we get into the black holes, real quick about where we live, where we are. Basically, we're in an average sized galaxy. There's a new piece of information that you may not be aware of. But the Milky Way galaxy is 13.6 billion years old, and its roots are from Romans Via Lactea, and Greeks called the galaxis kyklos, Milky Circle. Now, if we were doing this in person, this is where I normally would hand out Milky Way candy bars, but here we are, Zoom. It's a spiral galaxy with over 200 billion stars. Arguments are being made. It's in the 100 to 400 billion range. And by the way, this is not, I have been surprised by a number of people, I'm sure no one's in this crowd. This is not a picture of our galaxy. You see, that's as good as it gets, or better ones than this, but that's what our galaxy looks like from where we are. We cannot get out to be able to see our galaxy, so we interpret it based on how we see other galaxies and the information we have available to us. It's about 100,000 light years across, and we're located about 27,000 light years from the center in the Orion Spur. Somebody once said to me, a Professor Paul Trejo, that we're in the backwaters of the galaxy. I don't know how he knew that, but apparently he was sure. So here we are. And, well, we've talked about it, and we're going to talk about it some more. We have a supermassive black hole at the center of our galaxy, and we learn all these things. We do all these things. We measure all these things when everything is in motion. Think about that. Earth is rotating at 1,000 miles an hour. It's orbiting the sun at 66,000 miles an hour. It's orbiting within the Milky Way, and it's moving along. And the Milky Way is moving. All these different motions occurring, and we're out there being able to figure out how far away things are and how fast they're moving away from us. It is astoundingly amazing. A little update about the Milky Way. I'm seeing more and more as they go through the data. For centuries, we studied the Milky Way to get a better idea, right? What it looks like. Well, obviously that's pretty elusive because we can't go look at it. So we infer it based on what we see. And we can't see the galaxy, obviously, in its entirety. But we're pretty sure it's a barred spiral galaxy. I used to think the barred stuff meant this, like barbs. No, it's barred like this. This is what our galaxy theoretically looks like from the top down. but recent studies indicate something a little different. Astronomers from China and Australia did a study of Kefia stars. They measured 1,300 large pulsating stars, and what they were looking at was their positions and throughout the galaxy, and they're noticing their sort of like, if you look at the side of the galaxy, their positions, where they're located in the galaxy. And basically, they come across something that looks like this, which leads them to conclude that the Milky Way disk is not quite that flat. And it appears to be warped and twisted, and that we may actually, if you look at it from the side, it looks more like this. So I don't know what the conclusion is, right now, but I think the data points now to, this is what ESO thinks we look like. Here's there is a little bit of a curvature, a twist to it, a warp to it. It's not like right angles or anything like that, but it's interesting. And this is likely caused by massive disk and rotational forces or interaction with another galaxy before, or some of the dwarf galaxies near us. A variety. The root causes are not known. But the interesting thing is, warp galaxies are not uncommon. They're not that common, but it's not like we haven't seen them before. As Raj pointed out in his own talk, I think last month, that there's a universe of galaxies out there, and he's out there to hunt down hundreds of them. Maybe he's looked at 1,000 by now, but either way, there's a myriad of different types of galaxies out there. And but going back to us in our galactic neighborhood, I want to mention size again. Size is a big deal here. We're part of a local group on the outskirts of the Virgo galaxy cluster. There's the Milky Way galaxy. There's our bigger buddy, Andromeda. We've got somewhere in here, the other one is Triangulum. Now, I can't find it, but it's here somewhere. There's like 18 or 19 in our local neighborhood. And this is part of the Virgo supercluster. So, and there's our local group. You're getting an idea, think about it. There's the Milky Way, it's 120,000 light years across. And here we are in the known universe. It's massive. So the observable universe. I'm going to move on here to talking a little bit about what we can see and what we are able to observe. The universe is roughly 13.7, maybe it's 13.8, but let's stick with 7 billion years old. Then we should be able to see 27.4. In other words, treat it like a sphere in any direction, right? 13.7 times 2. But space is expanding. In fact, we've been the result of 2 major expansions. One was due to inflation very soon after the Big Bang, which is when one could argue, were we the size of a ping pong ball, the universe, or that of a big molecule or a grapefruit? And we expanded on the order of Planck time, meaning around 10 to the minus 30 seconds, to the size of a basketball. That would mean that we move way, millions, billions of times faster than the speed of light just to get to that side. But that's okay, because the laws of physics weren't established that early in the universe, and we could do that. And then it slowed down, it stopped, that inflation period, and we've been in this post-inflation expansion, and that's caused things to continue moving. So, it's like, regardless, when you're looking at how far away a truck is as it's driving away from you, well, every second is driving further and further and further away from you. And the universe is expanding, and it's moved things away. In fact, the observable universe, because of that initial expansion and leftover expansion, and it hasn't always expanded at the same rate, and then it's picked up. It's more like 93 billion light years across. The the universe. That's the observable. That doesn't mean it's the end of the universe. The end of the universe could be, who knows, infinite for all we know. You know, just because you can see, look out on a ship and see the horizon, doesn't mean that that's where the ocean stops. Well, that's what we are able to observe. So to give you an idea why understanding distances matter is because the observable universe is 93 billion light years across, 28 billion parsecs. Now, getting into that topic is a whole nother topic, so we're not going to get in there, but I just wanted to mention that. And space in law likelihood is infinite from what we know, or what we may not know also. So as huge as it is, I want to mention one really, the most important thing in the universe is us, of course, because there's nobody like us and there's nobody else out there as far as we know. So science tells us that nobody else has been found. So the most important living beings in the universe is us, and this is us right here, right? You've all heard of this pale blue dot. This photo was taken in February 14th, 1990. Voyager 1 was 39.8 AUs away, okay? Pretty far out. Look at that dot, as Carl Sagan said. That's us, that's everything. All of us, our past, 110 billion humans have died, and 8 billion roughly are alive today in our history as Homo sapiens. That's everything to us. So this is our place in the universe. And that's our family photo. But it's a big universe, right? The Milky Way galaxy, our past, our present, and our future are there. So as it builds in, I mean, these photos don't do it justice. Anyways, I'm gonna end that part of the conversation and move in quickly to talk a little bit about black holes and imaging. So I really wanted you to get a sense for, there is a method to the madness, how they measure distances, and it's very powerful techniques, and they're very accurate, and they overlap enough where we can cross-correlate and make sure that things are accurate. Black holes. I'm going to try to move a little more rapidly through this section simply because I want to be, you know, cognizant of your time as well. I know we start a little bit later. So it's the end result of the death of large stars, meaning stars that are bigger than our sun, several times bigger onwards from there. They collapse to, well, some would say zero volume, but beyond a certain point, we don't know. Our physics breaks down, our math breaks down. Remember, in physics and math, if the terms infinity creep in, that's bad news. So that's not good, but it's due to the gravitational forces that are involved with the high mass. So it results in, well, essentially infinite density. A singularity occurs, and density is simply mass per volume. And I put zero in quotes, but has beyond a certain point, we don't know what does that volume look like. You know, is it zero or is it 0.00001, whatever that is, in whatever units? But the density goes up phenomenally. And it's known for being sources of the strongest gravitational fields. John Wheeler, a physicist who helped divide, who also worked on the theories and around nuclear fission, he coined the name black holes back in a lecture in 1967. So now you know where the term came from. So a black hole is a location in space, basically where gravity is so strong, not even light can escape it. A star like our sun, light just exudes. A neutron star, which you're familiar with, or at least you probably heard about it, causing gravitational waves, can bend light, but can't suck it all back in. A black hole does that. Light will not escape from it. So these are exaggerated drawings, but you get the point. And because no light can get out, we can't see it directly. So It's typically formed from stars that are 3 to 15 times the solar mass. So we have a white dwarf, which is where we're headed. Our sun is just not big enough. I mean, the name of our sun is not name of our sun, but our stellar type. We're a dwarf star, a yellow dwarf star. Take that for what it means. A neutron star, and if it has sufficient mass, when it reaches beyond about 2.7 solar masses, it can become a black hole, all the way up to supermassive black holes. And the intermediate black holes can be anything in between that size. Theoretically, micro black holes can exist, okay? Meaning that if you could compress our sun into a black hole, it would form a black hole that's 3 kilometers in size. And if you did that to a human being, compress this down, well, me more than Raj, definitely, but I'd be a little bigger in the end, but it's on the order of 10 to the minus 25 meters. So, but we don't know that if they exist. These are all theoretical. Big ones can be on the order of billions of times our solar mass. So there are some huge ones out there. Remember, this is the size, Phoenix cluster, the central black hole this is the size of our entire solar system. And the black hole is, well, huge. So, and as it turns out, the center of our galaxy has a 4 million solar mass black hole. So here's, according to the European Southern Observatory, we have a black hole. Its structure looks like this. There's a photon sphere where these particles are so close to the point of no return, they want to go on a straight path, but they're curved because of the gravity. There's the innermost stable orbit where at least things can orbit, but these guys on the photon sphere are going to eventually work their way in. The accretion disk is all of this superheated material that that's orbiting the black hole. And the event horizon is known as the point of no return. And basically on this side of it, light can escape and you can see it, an object. On the other side of it, no, it can't. The escape velocity is equal to or greater than the speed of light. Therefore, nothing gets out. Jerry, I'll talk about the CMB at the end. Okay, the singularity is that point that's on the inside. This is where all of our math, science, our physics breaks down, because we don't know how things work on the inside of that. Unless you go see the movie Interstellar, it's a great interpretation. But it's a region of infinite density, general relativity, and quantum mechanics break down completely. And without quantum mechanics and general relativity, well, physics is just not that fun, because then all you're left with is pulleys and inclined planes. And I don't care how much you love those things. I do. I find them boring. Anyways, matter approaches and rotates into the accretion disk. This is a NASA video showing as things get eaten up. It can also, as the material is consumed, it can eject some of the material as high energy particles traveling at near the speed of light for thousands of light years, can eject it along that pole. Matter gets closer, it starts to orbit it. And as it gets closer, it starts to rub, they collide, they generate energy. And lots of times you get a whole bunch of X-rays, some gamma rays, and even radio waves will come off of that. There's some, visual stuff on the accretion disk, optical, but remember, it's all light. And in case, don't misunderstand me, when I say radio is light, microwave is light, infrared is light, and so is gamma ray. There's a little sweet spot that's designed for our eyeballs. And that's known as visible light to us, between infrared and ultraviolet. But it's all light as far as I'm concerned. So how do we detect it if we can't see it? Well, we look at the perturbed motion of nearby objects because a black hole doesn't sit quietly. If something is near it, it's going to impact it. It's going to cause gravitational lensing, meaning light gets bent around it, and so it looks like a lens effect. General relativity predicted it, and sure enough, it's true. And when he predicted it, they had no way of testing it until an eclipse in 1919. Arthur Eddington determined that. Emitted radiation, when material gets close, you get superheated material and you get X-rays. So that's at least a way of knowing where there might be a black hole, let alone you look at X-ray sources. That's why we have X-ray telescopes, one of the reasons. But radio telescopes look at the heart of the M87 and they're seeing something, including some jet materials out there too. And we have X-ray telescopes showing us all kinds of information that's occurring near a black hole, a wandering black hole. We can also look at that lensing effect that we're talking about. So there's a way of detecting, inferring the presence of a black hole, but we want to image it, right? That's what we're really after. Well, imaging a black hole isn't trivial. It is really hard work. And do not, before you ask, do not expect James Webb Telescope to go out there and look at our black hole at the center of the galaxy and see it. It doesn't have enough resolution. And I'll explain that in a minute. Imaging black holes requires some non-optical telescopes, right? X-ray telescopes, radio telescopes, things like that, because they're optically invisible. And so we image the energetic materials that's being ejected, that's emanating it in various forms of electromagnetic radiation, meaning some of it's visible, some of it's X-ray, some of it's radio waves, and so on. It requires large telescopes, preferably the size of our planet. That's why James Webb doesn't have enough resolution. And you need a bigger telescope. So in comes this last part, the Event Horizon Telescope. It's composed of a bunch of radio telescopes across the world, right? The neat thing is this, it's using existing telescopes in the US, in Hawaii, in Mexico, also at the ESO Southern Observatory. And there's one in Antarctica, and we've got in Spain and all over the world. We've got like 8 or 9 of these. I think they're getting up close to 12 now. And the Event Horizon Telescope is a collaboration, first and foremost. So what does that mean? It uses many telescopes. They're independent scopes that are synchronized. And I mean, when they go to look at something, each of these telescopes synchronized to within a billionth of a second. Because if I'm sitting over there a mile away and you're sitting a mile in the other direction, and we're supposed to say, detect something, we better know exactly what time it was that you saw what you saw and I saw what I saw. These things all need to be synchronized in a one-phased way. And this involves initially 300 scientists and 80 different countries. They're all collaborating together. And they use a technique called very long baseline interferometry, VLBI. And by acting as one together, they're basically an Earth-sized telescope, as I showed you in that drawing earlier. And because of the timing and the amount of data being generated after many days, many weeks of collecting the data, then you got to be able to now process the data. And it turns out it's got too much data to be able to transmit using something even close to an internet. So the data is collected, digital conversion from optical or radio data. Then all the atomic clocks are synchronized and verified. Hard disk packs are then flown to one location where basically supercomputers then take over and using artificial intelligence and machine learning software, start processing it into doing a data reduction and ultimately generating an image. So you need very specialized software. And remember, you're only taking, you've got these eight or 10 or 12, or when we imaged the first M87 black hole, we had 7 of these telescopes. When we went to Sagittarius, we have 8 of these now, and we have more coming online. So we can only get the little bits of data here and there. And I'll explain how that works in a second. But we can't, we don't have the ability to put tens of thousands of radio telescopes out there to image the entire black hole. So we just collect the data where we can and make sure everything is synchronized. But here's the neat thing. So as things start happening, this is sort of much later. So we collect some data here, collect some data here, data here, and data here, more than what's being shown in this short little video clip. As these satellites come into view of the black hole, I mean, if these telescopes come into view of the black hole, they collect this data. Okay, so now you've got this patchwork. Now, like I said, there'll be more of these red dots in the final product before they start putting it together. Then your software fills in the blanks. It's able to process it and fill in the rest of it, and then put the whole thing together into an image, and using false color. Remember, that's not an optical image of the black holes that we do see. And the first image, you know, before that could even happen, after 50 years of looking at basically artist conceptions of what a black hole is, we finally got it of M87 on April 10th, 2019. I was actually giving a lecture in quantum mechanics, and everyone wanted to talk about this. We spent 45 minutes on this that big day. It was a huge day because the first time we'd imaged a black hole. There's the accretion, I mean, the event horizons here. It's all black here, and there's all this accretion disk and material being ejected or rotating around the black hole. Remember, the black hole, or the singularity path after the event horizon, is spherical, and everything else is in a plane orbiting it. So this one is 55 million light years away, and it's 6.5 billion times the size of our sun. And by the way, observation versus computer models, up until then, not bad at all. So got to give them credit for their hard work. So at the same time, this is a home telescope that I had. This isn't from my telescope, an EV scope by Unistellar. That's what it looks like. And I was trying to compare that with what Wikipedia had to say with that. Obviously, I couldn't see the jets or any of that, but at least the home telescope was able to image that. That was fun doing some of that. But who cares, right? What about our black hole? We're almost to the end. The center of the Milky Way has a 4 million solar mass black hole. So we've been staring at it for a while using X-rays from the Chandra telescope and the Hubble telescope. And somewhere out there, just looking into it, along the side of the galaxy, 27,000 light years in there. Well, we started looking at mapping the stars. NASA started doing this, and along with other research institutes, looking at the eccentricities of these stars orbiting something big. Then they started in 1995 looking at the star is the black hole, and looking at the paths of various stars around it. So that type of motion, given the spectroscopy of all these stars, we knew how big they were, how massive they were, and types of orbit they were. They were orbiting something we couldn't see, something that was 4 million times the sun, a gravity well that big. Well, so that was a big deal. So after M87, we needed to finally image, well, we did at the same time, but it took a lot longer to process the data, or they were back to back in 2017. And this is what you saw last week. This is our star, our black hole. and it was composed of a number of different images that were taken, and here's the net result. Now, M87 is much farther away, 55 million versus 27,000 light years. Sagittarius A star is much smaller, 4 million solar masses versus 6.5 billion solar masses. But here's the cute and cool thing. Look at the size difference. So this is Pluto's orbit, and Sagittarius A star goes out to Mercury's orbit, and you can see M87 is bigger than our, well, solar system. But here's this cool thing. They're very similar. That means our black hole theories make sense. Size didn't change things so that they were very different. One may have an ejecting at the poles, a bunch of particles, but they're behaving the same way. So our theories are holding up. And remember, our black hole is a lot harder to image. Matter rotates around it much faster, hours versus days on M87. And that's like trying to take a sports photo when you got the whole thing set for, 1/30th of a second, and race cars are going by. And so things get blurry. Material is rotating much, much, much faster in our black hole than on M87, which rotates around in days and weeks. Visibility is obscured by dust, gas, and all that. We can look head on to M87 through interstellar space with nothing in the way. Easier to see. 6.5 billion times bigger. Notice as a result, M87 is actually a much clearer, crisper photo image than Sagittarius A star. This was released in 2019. This is released now because it took a lot more work to process this. Okay, so there is that difference. And I think you can see it to some extent. So they're out there looking at other black holes to image. They're looking at telltale signs when they're finding them, effect on another star, birth of a black hole after a supernova failed. NASA did some simulations and showed, how stars end up shredding in another star that comes by, and the material that's ejected. I know we're running out of time, so I won't go into it too much here. We don't need to see all 138 days. This one I'm going to skip. This is about a failed, if anyone ever wants, I can give you a link to it. But this is about a failed
For the first
supernova.
time ever, astronomers might have witnessed a star actually become a black hole right before our eyes, or telescopes. In this visible
So we'll skip this for now. Also, up until, well, for a long time, we thought black holes would live forever. But as it turns out, theories have shown that maybe it won't. And quantum theory suggests that there are pairs of virtual particles, matter and antimatter, that use vacuum energy and can come in and out at any given point. But the problem is that they don't live long enough. As soon as one pops in, a matter and antimatter particle, they annihilate each other. So what I'm trying to say is, in a vacuum or at any given time, a particle can pop out of a virtual particle and just pop into existence with this antiparticle. The two will annihilate each other and everything is fine. It happens very quickly. So things like, how did energy get created out of nothing? Conservation of energy is preserved because of the short time scales. But the theory goes that when this happens, they'll annihilate each other, which is fine. But at the event horizon of a black hole, if it turns out, as Stephen Hawking predicted in 1974, that if these virtual particles are created out here, they'll find each other and annihilate each other. If they're very close, one particle escapes as radiation, and the other one gets absorbed and known as a negative energy, and then will reduce the mass of the black hole because it's presumed to have negative energy. This is a very high level way of saying how this process works. But the point is that if this pair is produced next to the event horizon, it's possible that one particle gets absorbed and the other particle comes out as radiation that we would see coming out of the black hole, which we now call Hawking radiation. And the negative particle that ends up in there, by being absorbed by the black hole, reduce its mass. And if you reduce the mass of a black hole, it'll eventually evaporate, it'll collapse. This is fairly theoretical stuff, but the math works. What's interesting is 3 or 4 or 5 different ways have been looked at this thing besides the way Stephen Hawking did, and the same conclusions were reached. So all the math works, we just haven't detected it. What happens here, why it reduces the mass, we don't know. And we won't know until, well, the grand unification theory is formed, meaning quantum mechanics and general relativity play nice with each other, and they don't play nice with each other. It looks like, maybe general relativity will be changed down the road, but so far that hasn't been a problem. But I just want you to know, theoretically, black holes can evaporate and die off. So it requires 3 or more solar masses to become a black hole. The smallest could be as large with the mass of a mountain, the size of an atom, but that's all theoretical. Many stellar black holes are 20 times the mass of our sun, and supermassive black holes are, greater than 1 million to billions of times. And then we've already talked about that. What I need you to remember is this: general relativity rules. Einstein predicted this. Now we've got photos to prove it. Okay, let's face it. Him and his trippy math, once again, they win. I have yet to see him being proven wrong. I had more slides in a later one, but we're out of time. So I really want to thank you for your time. And I'm a big fan of Gary Larson and the Far Side. So if any of you have any questions, I would be happy to take them. I'm going to unshare. So that's my lecture or my talk. I hope you found that interesting. Any questions, please feel free to chime in.